Our next keynote speaker is going to help us see where we are in the journey towards human-level AI. Yann LeCun is the Chief AI Scientist for Facebook AI Research, or FAIR. He's a professor at NYU. He is the recipient of many awards, including a 2018 ACM Turing Award. He's a member of AAAI, National Academy of Engineering. Please join me in welcoming Yann LeCun to the stage.
Thank you, Talia. Yeah, the F in FAIR doesn't mean Facebook anymore.
Oh, I'm so sorry.
It means fundamental. But who cares? Okay, so I'm going to talk about human-level AI, or how do we get there, and how we are not going to get there as well. So first of all, we do need human-level AI because there is a future in which most of us will be wearing smart glasses or wearing other types of devices, and we'll be talking to them, and those systems will host assistants, maybe not just one, maybe a whole collection of them. And what that will cause is that all of us will have basically a staff of kind of smart virtual people working for us. So it's like everybody would be a boss, just not of real humans. And we need to build this for basically amplifying human intelligence and, making people more creative, more productive, and everything. But for this, we need machines that understand the world, they can remember things, that have intuition, have common sense, things that can reason and plan to the same level as humans. And despite what you might have heard from some of the most enthusiastic people, current AI systems are not capable of any of this. So that's what we need, systems that learn to basically model the world, have mental models of how the world works. And every animal has one such model. Your cat certainly has one that's more sophisticated than any AI system ever built or ever devised. Systems that have persistent memory, which current LLMs don't have. Systems that can plan complex action sequences, which is not possible with LLMs today. And systems that are controllable and safe. So I'm going to be proposing an architecture for this that I call objective-driven AI. I wrote kind of a vision paper about this that I posted about 2 years ago. And a lot of people at FAIR are basically working towards implementing that plan. FAIR used to have a combination of, kind of long-term blue sky research and kind of more applied projects. But Meta, a year and a half ago, created a product division called Gen AI, focused on AI products. And they do applied R&D. So now FAIR has been sort of redirected towards the longer term, next generation AI system. We don't do LLMs, basically. So the success of AI, including LLMs, including a lot of other systems, over the last 5-6 years, has hinged on a set of techniques that I've called self-supervised learning. And one way to use self-supervised learning, so self-supervised learning consists in training a system not for any particular task, but basically training to sort of represent the input in a good way. And one way to do this is through reconstruction from corruption. So you take, let's say, a piece of text, you corrupt it by removing words or changing some of the words. And it can be text, or it can be DNA sequences or protein or whatever it is, or even images to some extent. And then you train a gigantic neural net to reconstruct the full input, the uncorrupted version. Okay? And that's a generative model because it attempts to reconstruct the original signal. So those, this is meant to be, okay, but it doesn't project. So the red box is like a cost function, right? It computes the distance between the input y and the reconstruction y tilde. And that's what the learning minimizes with respect to the parameters in the system. Now, in the process of doing so, the system learns an internal representation of the input that can be used for all kinds of subsequent tasks. It can be used, of course, to predict words in the text. And that's what happens with autoregressive prediction. So LLMs are a special case of this, where the architecture is designed, oops, and I'm not sure why this thing is flipping by itself. A particular architecture where the thing is designed in such a way that to predict an item, a token, or a word, it can only look at other tokens that are to the left of it. It cannot look into the future if you want. So if you train a system to do this, right, you show it a text, and you ask it to predict the next word in the text or the next token. Then you can use the system, of course, to predict the next word. And then you shift that next word into the input, and then predict the second word, and shift that into the input, predict the third word. That's autoregressive prediction. And this is what LLMs do. It's not a new concept. It's been around with us since Claude Shannon, so it goes back to the 50s. That's a long time. But what's changed is that now we have those gigantic neural net architectures that we can train on enormous amounts of data, and it looks like some properties emerge from that. Okay, but that autoregressive prediction has some major limitations. So there's no real reasoning in the usual sense of the term here. And there is another limitation, which is that this only works for data that comes to you in the form of discrete objects, symbols, tokens, words, things that you can discretize, essentially. And we're still missing something big to reach human-level intelligence. And I'm not necessarily talking about human-level intelligence here, but even your cat or your dog can do amazing feats that are still completely out of reach of current AI systems. How is it that any 10-year-old can learn to clear up the dinner table and fill up the dishwasher? And the 10-year-old can learn this in one shot, right? There's no need to practice or anything. 17-year-old can learn to drive a car in about 20 hours of practice. We still don't have level 5 self-driving cars. And we certainly don't have household robots that can clear up the dinner table and fill up the dishwasher. So we're really missing something big, right? Otherwise, we would be able to do those things with AI systems. So we keep bumping into this thing called the Moravec paradox, which is that things that appear trivial to us, that we don't even consider intelligent, seem to be really, really difficult to do with machines. But like high-level, complex, abstract thinking, like manipulating language, seems to be easy for machines, or things like playing chess and Go and stuff like that. Okay, so maybe one reason for this is the following. An LLM is typically trained on 20 trillion tokens. A token is basically is like 3/4 of a word on average for a typical language. So that's 1.5 10 to the 13 words. Each token is about 3 bytes, typically. So that's 6 10 to the 13 bytes. It would take, on the order of a few 100,000 years for any of us to read through this, right? That's the totality of all the text available publicly on the internet, essentially. But then consider a human child. A human child, a 4-year-old, has been awake a total of 16,000 hours, which, by the way, is 30 minutes of YouTube upload. We have 2 million optical nerve fibers, optic nerve fibers coming to our brain. Each fiber roughly carries about 1 byte per second. Maybe it's 1/2 byte per second. Some estimate it's like 3 bits per second. Doesn't matter, it's an order of magnitude. So that data volume is about 10 to the 14 bytes, roughly the same order of magnitude as the LLM. So in 4 years, a child has seen as much visual data as the biggest LLM trained on the entire publicly available text on the internet. So that tells you a number of things. That tells you, first, that we're never going to reach anything close to human-level intelligence by just training on text. It's just not going to happen. Then the counter-argument is, okay, but visual information is very redundant. So first of all, this 1 byte per second per optic nerve fiber, that's already a 100-to-1 compression ratio compared to the photosensors you have in your retina. We have on the order of 60 to 100 million photosensors in our retina, and that gets compressed using neurons in front of your retina to 1 million nerve fibers. So there is already a 100-to-1 compression. Then it gets to the brain, and then it's expanded by a factor of 50 or something like that. So I'm measuring compressed information, but it's still very redundant. And redundancy actually is what self-supervised learning requires. Self-supervised learning will only learn something useful from redundant data. If the data is highly compressed, which means it's completely random, you can't learn anything. You need redundancy to be able to learn anything. You need to learn the underlying structure of the data. So we're going to have to train systems to learn common sense and physical intuition by basically watching videos or by living in the real world. I'm going to maybe go a little bit in out of order and then tell you a little bit about what this objective-driven AI architecture really is. And it's quite different from things like LLM or feed-forward neural nets in the sense that the inference procedure is not just running through a bunch of layers of a neural net, but it's actually running an optimization algorithm. So conceptually, it looks like this. A feed-forward process is a process by which you see an observation, run through perception system, for example, a bunch of layers of neural net and produce an output. You can only have one output for any single input. But there are a lot of situations for which there are multiple possible outputs, interpretations for a percept. And you'd like a process that does not just compute a function, but computes a mapping that might have multiple outputs for a single input. The only way you can do this is through implicit functions. Basically, a function like this objective here, the red box on the right, which basically measures the compatibility between the input and a proposed output, and then computes the output by finding one value of the output that is most compatible with the input. And you can do this by imagining that this objective is some sort of energy function, and you're minimizing this energy with respect to the output. You might have multiple solutions. You might have some way of going through those multiple solutions. The human perceptual system does this. If you have multiple interpretation of a particular percept, your brain spontaneously will actually cycle through those interpretations. So there's some evidence that things of that type can take place. But let me go back to the architecture. So using this principle of inference by optimization, the way, the hypothesis of the way people think, if you want, is the following. You make an observation in the world. A perception system gives you an idea of the state of the world, the current state of the world. But of course, it only gives you an idea of the state of the world you can currently perceive. You might have some idea about what the rest of the state of the world is from memory. So that might be combined with the content of a memory. And that's fed to a world model. What is a world model? A world model is your mental model of how the world behaves. Okay, so you can imagine a sequence of actions that you might take. And your world model will allow you to predict what the effect of the sequence of action will be on the world. So the green box, the world model, you feed it a hypothesized sequence of actions, and it predicts what the end state of the world is going to be, or it predicts the entire trajectory of what's going to happen in the world. You feed this to a bunch of objective functions. One objective that measures to what extent a goal has been achieved, a task has been fulfilled, and maybe a set of other objectives that are guardrails, things that basically measure to what extent the trajectory that has been followed or the actions that have been taken are things that are not dangerous for people around the robot or the machine, etc. So now the inference process, I'm not talking about learning yet, it's just inference, consists in finding the action sequence that minimizes those objectives. Finding a sequence of actions that minimizes those objectives, okay? That's the inference process. So it's not just feed forward. You can do this by, searching through discrete options, but that's inefficient. A much better way is to make sure that all of those boxes are differentiable and you backpropagate gradient through them and you update the action sequence through gradient descent. Now this idea is very, very far from being new. It's over 60 years old, if not more. And it's based on, okay, so first let me talk about the advantage of doing this kind of inference using a world model. The advantage is that you can basically accomplish new tasks without requiring any learning. We do this all the time. We're faced with a new situation. We think about it. We imagine the consequences of our actions. And we take the sequence of actions that will fulfill our objectives, whatever it is. We don't need to learn to accomplish that task. We can plan. Okay, so this basically is planning. You can reduce most forms of reasoning to optimization as well. So this process of inference by optimization is intrinsically more powerful than just running through a bunch of layers in a neural net. Now this idea that you do inference by optimization is, as I said, has been around for over 60 years. In the optimal control theory field, it's called model predictive control. You have a model of the system you're trying to control, let's say a rocket or something, or an airplane, and you can, or a robot, and you can imagine, you can compute using your world model the effect of a sequence of controls, commands, and then you optimize the sequence so that the motion does what you want. All classical robotics, motion planning is done this way, okay? Not a new thing. What's new here is we're going to learn the world model, and we're going to learn the perceptual system that is going to extract an appropriate abstract representation of the situation, of the world. Now, out of this, before I go into an example of how this can be run, you can build an overall kind of AI system that has all of those components, the world model, the cost functions that can be configured for the task at hand, the actor, which is the module that really optimizes, finds the optimal sequence of actions given the world model, the short-term memory, perception system, etc. So how does that work? So if your action is not a single action, but an action sequence, and your world model is really a system that tells you, given the state of the world at time t and an action I might take, predict the state of the world at time t plus 1, and you want to predict what a sequence of two actions, in this case, will produce, you can run your world model multiple times, right? So here it's represented as unfolded in time, get the initial world state representation, feed a hypothesis for action 0, use a world model to predict the next state of the world, then action 1, next state of the world, compute the cost, and then through backpropagation and gradient-based optimization method, figure out the two actions that will minimize the cost. Okay? That's model predictive control. Now, the world not being completely deterministic in general, you might have to use latent variables to feed to your world model. So latent variables are basically variables that can swipe over a set or be drawn from distributions, and they represent, they basically cause the world model to swipe through multiple predictions that are compatible with the observation. The world is not entirely predictable, and so you might need to deal with this type of uncertainty when making predictions. What's more interesting is to do what humans seem to be capable of doing, and certainly a number of animals, and it's hierarchical planning. So if you're planning a trip from, let's say, New York to Paris, you could be using your world model, the model of your own body, and maybe your idea of the entire configuration of the world from here to Paris, to plan your entire trip in terms of your low-level muscle control. But of course, nobody does that. You can't do it. You don't even have the information to do it. And it would be kind of crazy, right? The number of steps every 10 milliseconds of muscle control that you had to do before you go to Paris, is just insane. So what you do is you plan hierarchically. You go at a very high level, and you say, well, to go to Paris, I first need to go to the airport and catch a plane. How do I go to the airport? I'm in New York City, let's say. I have to go down in the street and hail a taxi. How do I go down in the street? Well, I have to raise from my chair, move to the door, open the door, go to the elevator, push the button, blah, blah, blah. How do I get up from my chair? At some point, you're going to have things that can be expressed in terms of low-level muscle control actions. But we're not planning the entire thing in terms of the low level. We're doing hierarchical planning. How to do this with AI systems is completely unsolved. We have no idea how to do this. And that seems like a pretty big requirement for intelligent behavior. So, how are we going to learn world models that are hierarchical, work at several different levels of abstraction, and allow us to do this kind of hierarchical planning. Nobody has demonstrated anything close to this. That's a big challenge. Yeah, it's just a pictorial representation of the example I just said. Okay, so how are we going to train this world model now? Because that's really kind of the big challenge. And you look at babies, but this is true for animals as well. And psychologists, cognitive scientists, I've tried to figure out at what age babies learn basic concepts about the world, like how do they learn, intuitive physics, physical intuition, all that stuff. This happens long before they start to learn about language and interaction and things like this. So things like face tracking happen really, really early, biological motion, the fact that there is a difference between animate and inanimate object, that happens pretty early too. Object permanence happens really early. The fact that when an object is hidden by another one, it still exists. And then, babies learn like natural kinds of categories. You don't need to give them names of things. They will know that a chair and a table and a cat are different. Stability and support. But things like gravity, inertia, conservation of momentum, that actually only pops up around 9 months, roughly. That takes a long time. So if you show a 6-month-old the scenario on the left here where a little car is on a platform and you push it off the platform and it appears to float in the air, 6-month-old baby will barely pay attention. A 10-month-old baby will go like the little girl. She's understood that it shouldn't happen. The object should fall. And when something surprising happens, that means your world model is wrong, so you pay attention. Because it could kill you. So the type of learning that needs to happen here is very similar to the type of learning that we were talking about earlier. Okay? Take an input, corrupt it in some way, and train a big neural net to predict what's missing. If you train a system to predict what's going to happen in a video, the same way we train neural net to predict what's going to happen in text, maybe those systems will be able to learn common sense. The bad news with this is that we've been trying to do this for 10 years, and it's a complete failure. Okay? We've never been able to get anywhere close to systems that really learn any kind of, generic knowledge about the world by just trying to predict the pixels in a video. You can train a system to predict videos that look nice, and there are a number of examples now of video generation systems. But internally, they are not good models of the physical world. They cannot use them for that. Okay, so this idea that we're going to use generative models to predict what's going to happen in the video and the system will magically understand, the structure of the world, complete failure. And we tried many things over 10 years. The reason it's a failure is because there are many possible futures. And in a discrete space like text, you cannot predict which word is going to follow a sequence of words, but you can produce a probability distribution of all possible words in a dictionary. But when it's video frames, we do not have a good way to represent probability distributions over video frames. And in fact, the task is completely impossible. Like if I take a video of this room, right? I take a camera, I shoot that part, and then I stop the video and I ask the system to predict what's next in the video. It might predict that there's going to be the rest of the room. At some point, there's going to be a wall. There's going to be people sitting. The density is probably going to be similar to what's on the left. But it cannot possibly predict at the pixel level what all of you look like, what the texture of the wall looks like, and the precise size of the room and all things like that. There's no way you can predict all those details accurately. So the solution to this is what I call joint-embedding predictive architectures. And the idea is to just give up on predicting pixels. Instead of predicting pixels, let's learn a representation, an abstract representation of what goes on in the world, and then predict in that representation space. Okay? So that's the architecture, joint-embedding predictive architecture. There's two embeddings. Take X, the corrupted version, run it through an encoder. Take Y, run it through an encoder. And then train the system to predict the representation of Y from the representation of X. Now the question is how you do this, because if you just train a system like this using gradient descent backpropagation to minimize the prediction error, it's going to collapse. It's going to say, it's going to learn a representation that is constant, and now it becomes super easy to predict, but it's not informative. But that's the difference that I want you to remember, the difference between generative architectures that try to reconstruct predictors, autoencoders, generative architectures, masked autoencoders, whatever, and then the joint-embedding architecture where you make predictions in representation space. The future, I think, is in those joint-embedding architecture. We have tons of empirical evidence that to learn good representations of images, the best way to do it is to use those joint-embedding architectures. All attempts at trying to learn representation of images using reconstruction are bad. They don't work very well. And there were huge projects on this and claims that they work, but they really don't. The best performance are obtained with architecture on the right. Now, if you think about it, this is really what we do with intelligence. Finding a good representation of something or phenomenon so that you can make prediction is really the essence of science, really, right? Like think about the fact that if you want to predict the trajectory of a planet is a very, very complex object. It's enormous. It's got weather and temperature and density and all kinds of things you can measure about a planet. It's maybe an incredibly complex object. But to predict the trajectory of a planet, you only need to know 6 numbers, 3 positions and 3 velocities. That's it. You don't need to know anything else. So that's a really kind of important example to really demonstrate the fact that the essence of the ability to predict really is to find good representations for things we observe. So how do we train those things? So this is okay, how do we train those things? So you want to prevent the system from collapsing. So one way to do this is to have some sort of cost function that measures the information content, if you can, of the representation coming out of the encoder, and try to maximize the information content or minimize the negative information, which is what's written here. So you're training a system to simultaneously extract as much information from the input as possible, but at the same time, to minimize the prediction error in that representation space. So the system is going to find some sort of trade-off between extracting as much information as possible, but not extracting information that is not predictable. Okay? You're going to get like a good representation in which space in which you can predict, you can make predictions. Now, how do you measure information? And that's really where things become a little weird. Okay, I'm going to skip this. Well, there is a way to understand this mathematically in terms of training energy-based models and energy functions, but I don't have time to go into this, but basically I'm telling you a number of different things here. Abandon generative models in favor of those JEPA architectures, abandon probabilistic models in favor of those energy-based models, abandon contrastive methods. I didn't talk about this because I'm going to come to this in a second, and also reinforcement learning, but I've been saying this for 10 years. And so these are all 4 most popular staples, pillars of machine learning today, so I'm not very popular at the moment. Okay, so one way to do this is to have some estimate of the information content that comes out of an encoder. And there is half a dozen different methods for doing this at the moment. There's one actually missing here called MMCR from my colleagues at NYU and Flatiron, actually. So one idea here is prevent the system from just collapsing and producing constants, right? So take the variables that come out of the encoder and make sure that those variables have non-zero standard deviation. You can put this in a cost function over a batch of samples, make sure that the weights are such that the variables don't collapse and become constant. That's easy enough. Now, the problem is that the system can cheat and make all the variables equal or very highly dependent or correlated. So what you have to do is add another term that says, I want to minimize the off-diagonal terms of the covariance matrix of those variables to make sure that they're correlated. And of course, that's not enough because the variables could still be dependent, dependent but not correlated. So we use another trick, which is to expand the dimension of Sx into a higher dimensional space Vx, and then apply this variance covariance regularization in that space. And that seems to be enough. But there is a trick, like I fooled you, or some of you, because what I'm maximizing here is an upper bound on information content. And I'm crossing my fingers that the actual information content will follow my maximization of the upper bound. What I would need is a lower bound. So I would push up on the lower bound and the information would go up. Unfortunately, we don't have lower bounds on information. Or at least we don't know how to compute it if we have them. There's a second set of methods. It's called distillation style methods. And that method works in mysterious ways. If you really want to have a clear explanation for why it works, you should ask Surya Ganguly, who is sitting right here. He has a paper on this. Personally, I'm dumbfounded, but it works really well. And it consists in only updating one half of this architecture and not backpropagating gradient on the other half and then sharing the weights in a funny way. There's a bunch of papers on this. It works really well if you want to train a system completely self-supervised to learn good representations of images. This is as good as any. And where the corruption of the images is by masking. We have some more recent work where we do this for video, so we can train a system to basically extract good representations of video that we can use for a downstream task in action recognition in video and things like this. And it consists in taking a video, masking a big chunk of it, running through this thing, and doing prediction in representation space and using this distillation trick to prevent collapse. And this works really well. Okay, so in the future, all of our interaction, if we succeed in this program and eventually get to systems that can reason, can plan, can understand the physical world, it's going to take years, right, before we get everything here to work, if not a decade. Mark Zuckerberg keeps asking me how long it's going to take. So if we succeed in doing this, okay, we're going to have systems that really will mediate all of our interaction with the digital world. They will answer all of our questions. They will be with us at all times. They will basically constitute a repository of all human knowledge. And this feels like an infrastructure kind of thing, like the internet, right? It's not like a product. It's more like an infrastructure. These AI platforms must be open source. I don't need to convince anybody from IBM here because IBM and Meta are part of something called the AI Alliance, which promotes open source AI platforms. But, and I really thank Dario for spearheading this and everybody at IBM. So we need those platforms to be open source because we need those AI systems to be diverse. We need them to understand all languages in the world, all cultures, all value systems. And you're not going to get that out of a single assistant produced by a company on the West Coast or the East Coast of the US. This will have to be contributions from the entire world. And of course, it's very expensive to train a foundation model, so only a few companies can do this. So if those companies like Meta can provide those base model in open source, then the entire world can fine-tune them for their own purpose. So that's kind of the philosophy that Meta has adopted, and IBM as well. So open source AI is not just a good idea, it's necessary for cultural diversity, perhaps even the preservation of democracy. Training and fine-tuning will be crowdsourced or will be done by the ecosystem of startups and other companies. And this is really what has jump-started the ecosystem of AI startups, is the availability of those open source AI models. How long is it going to take to reach human-level AI? I don't know. Could be years to decades. There's a huge variance. And there's many problems to solve on the way, and it's probably almost certainly harder than we think. It's not going to happen in one day. It's going to be like progressive evolution. So it's not like one day we're going to discover the secret to AGI and we're going to turn on a machine and immediately we'll have super intelligence and all of us will be killed by a super intelligent system. No, it's not happening this way. Machines will surpass human intelligence, but they will be under our control because they will be objective-driven. We give them goals, and they fulfill those goals. It's just like many of us here are leaders in industry or academia or whatever. We work with people who are smarter than us. I certainly do. There's a lot of people working with me who are smarter than me. Doesn't mean they want to dominate or take over, right? So, so that's the story. There is risk, but I'm going to leave that for the question session. Thank you very much.